Welcome back to ECE 442-542. Our first exam is in a week, so be ready for that. I think we will probably have more people in attendance on that day, so you may want to make sure that you get here on time so that you can find a chair to sit in. There is review material on D2L, but if you have a particular topic or questions you would like addressed during the review session, there's a quiz on D2L and you can submit your question or topic on that. The review session is scheduled in this room for this review session. I don't know if that will be the case in subsequent review sessions. We have to request rooms for those special events. But for Monday's review session, it will be in this room. Homework number 2 is due on Monday. Question? What we learn on Monday will probably help you on the exam, which means maybe you'll want to, well, Monday has not only a lecture, but it also has a review. So in general, what you learn on Monday will definitely help you on the exam. But the new material, who knows if we'll have new material. Depending on how many questions I have today, I may be trying to make up time on Monday's lecture. Question? I don't even want to repeat the question, but the question was, is the exam extra credit? And no, it is not. If you look at the syllabus, you'll see what fraction of your grade concerns the exam. And unfortunately or fortunately, a fair amount of your points for the semester are for exam number 1, which is a week from tonight. Today what I want to do is cover really 2 main things. One is to quickly just present some Z-transform properties or theorems, ways that might help you get to an answer quicker. And the next piece of tonight's material is concerning how do we create a low-pass filter for a digital system, or can we design that? And it will end up being just this linear difference equation, and now you can easily filter a signal. If somebody gives you this string of numbers, you can now put it into this difference equation and generate a low-pass filtered version of that waveform. And we'll try to build that or create that or design that low-pass filter based on where we maybe or should already be comfortable, and that's with the continuous time low-pass filter. And we'll step through that development. And that's really a discrete equivalent process, and that will be further explored later on this semester. But it starts to get us comfortable with the transfer function and this difference equation and the connections. And then the next lecture we'll probably talk, or maybe even today, about the frequency response, which we will, I think, of a discrete time system. How do we find that, and what does it look like? Let's start then with Z-transform theorems. This is the definition of the Z-transform, and it's really just a way of weighting this sequence of time domain numbers that are captured in little x of n, and we weight it by this complex exponential. Z is a complex number, and we know how to make some of those geometric series converge by looking at this common ratio, and that then gives us our region of convergence. But what we want to talk about now are some of these theorems that might allow us to obtain a result quicker than not. And the first one is a property or a theorem of linearity, which says that if you're looking at a Z-transform of some linear combination of 2 sequences, let's say it's sequence f sub 1 of the argument little n capital T and another weighted sequence f sub 2 of nt, the Z-transform is a linear operator, meaning we can now factor out that scaling from each of these pieces, and we can really separate the Z-transform operation through that summation. So that now we have alpha times the Z-transform of f sub 1 of nt plus alpha sub 2 times the Z-transform of f sub 2 of nt, or that's now just alpha 1 f sub 1 of z plus alpha sub 2 f sub 2 of z. And that now allows us, if we can identify an f sub 1 and a little f sub 2 within a given time sequence, and we know the Z-transforms of little f sub 1 and little f sub 2 separately, it's maybe a very quick process to find the sum, or this weighted sum, of Z-transforms, to find the overall Z-transform. Another theorem that you've heard for the continuous time case, and it also has its counterpart in discrete time settings, and that's convolution, where if we now look at the Z-transform of a convolution in the time domain of two discrete time signals, let's say f sub 1 of L and f sub 2 of n minus L, we could find that in the frequency domain by just taking the product of the Z-transform of little f sub 1 and the Z-transform of little f sub 2. For this discrete time convolution, Z-transforms into the product of the individual time domain waveforms Z-transforms. And that's consistent with what you're used to seeing for the continuous time case. And that's a lot of times why we like to go into the frequency domain. We don't have to worry about this convolution in the time domain. It's now consistent with a product in the frequency domain. One of these theorems that we've already been using, and you will use all the time in this class, is the time shift theorem, which says that if we look at the Z-transform of a time sequence f, and now let me try to identify what these different variables represent in the argument of f. Let's say that little n is in fact our time index. That's the one that is then moving from 0 to 1 to 2 to 3. It's moving along, or starting at minus infinity and coming up. And little l, that's now a fixed integer. And let me just go ahead and put the two together. We could either have n plus L or n minus L, and that now corresponds to, in the frequency, or if we Z-transform that time domain expression, let me close up the bracket, that now is this Z weighted version, and let me be consistent with my colors, of plus or minus the fixed integer offset in this time sequence times, or weighting, the Z-transform of the unshifted f of n. Meaning you can think of little f of n as some shifted sequence of values. Maybe it's a delayed amount where we would then have little f's of n minus 2. And we've Z-transformed that before. That's now z to the minus 2 times the Z-transform of little f of n. This one you use all the time, or we have. And when we try to Z-transform or take the Z-transform of a difference equation, then we're using this time shift theorem quite often. Another theorem that might be useful is what we will call scaling in the Z-plane. Which says then that the Z-transform of r to the minus n f of n, now we're weighting the original time domain waveform little f of n by some r, that's a constant, raised to the minus n power. And n, again, is our time index, so that will then scale f of n appropriately relative to the time sequence value, little n. This now becomes the Z transform of f r of z. Let's just look at an example of that, or how that might play out. Suppose that we have little f of n is now a to the n. And a in previous lectures might have been capital R. We're just looking at a number, say capital A is 1/2. Now we have 1/2, 1/4, 1/8, etc. as a function of time. This now, do you remember what its Z transform was equal to? If A was R, do you remember what we derived last time? This is now an exponential decay if A is less than 1, or R is less than 1. And what was the Z transform of that A to the n? Do you remember? Where was the pole? These things in a week's time need to just roll off your hand. I was going to say roll off your tongue, but I don't need you to be talking during the exam. I want it to be just flowing from your brain right down onto the paper. This now Z transforms into Z over Z minus A. Remember, it was 1 over 1 minus the common ratio. So you could do this Z transform definition and then very quickly figure out what that Z transform was. Suppose now that somebody, you knew this relationship, and now somebody says, oh, little g of n is related to little f of n by a modification with n, and r is now a fixed value. So if you want, you could plug in some numbers. Suppose, and I've been saying let a equal 1/2 and little r equal 1/2 if you wanted to, or no, not 1/2. Let me make it something that's easier to think about. Let's make r equal to 4. So that now we really, if you plug in r equal to 4, g of n is now just a over 4, that quantity raised to the n. So if a was 1/2 before, now that whole thing is 1/2 divided by 4, or 1/8. And you should see that that's now collapsing even faster. Well, to use this particular theorem, that says that, oh, this is in fact, can be rewritten to be consistent with the theorem's expression. And that says then that if we use this theorem, the Z transform of little g of n, now everywhere I see a z in f of z, I replace it with rz. Or now I have z in the numerator, that would now be rz. In the denominator I have a z, and that's now rz minus a. And you can show that it's consistent with what we just said when g of n was really this 1/8 to the n. We should get z over z minus 1/8 if we plugged in a equal 1/2 and r equal to 4. Here, let's factor out the r from the denominator. Cancel the r's in the numerator and denominator, and we end up with an expression for the Z transform of little g of n consistent with what we would have anticipated for that particular case. Meaning, if you can now identify an f of n in your original expression and then a factor r that's different, you could now quickly find the Z transform of that G of n, little g of n, if you knew the Z transform of the original f of n. By everywhere you see a z, you replace it with rz. So that's a scaling in the z-plane. You're now sort of expanding or contracting based on what r is in that Z transform. One more. Let's look at the final value theorem. Again, we have to have conditions when we can apply this. Just like in the continuous time case, we had to make sure that certain factors in our denominator were present or not present. Here, let's say now that if capital F of z, that's the Z transform of little f of n, converges for the magnitude of z bigger than 1, that says our region of convergence is outside of 1. That's what that's saying. And all the poles of z minus 1 times f of z are stable or inside the unit circle, then we can apply the final value theorem, which says that the limit of our time domain waveform, little f of n, as n marches off to infinity, can be found by looking at the limit as z approaches 1 of z minus 1 f of z. Meaning, if you just need to know what's my final value of this time domain waveform, and somebody or you already have access to the Z transform of that waveform, you don't have to inverse Z transform and then look at the limit as n goes to infinity. You can simply apply this relationship as long as the conditions are met, and you can quickly find where you're going in the limit of your time domain waveform as n marches off to infinity. Those are some theorems that are there to help you get to an answer more quickly or more effectively or more efficiently. Let's now move on to the next topic, which is really how do we interpret or how do we look at frequency response in the discrete time setting. How did you do that in the continuous time setting? Do you remember what we would do in the continuous time setting? And now I have to go over to the table. Remember, if we excite a system with a sinusoid, what happens? If it's a linear system and it's stable, what's going to happen at the output? If we're now injecting a sinusoid into this linear system, what comes out at the output? What do you see after the transients have decayed? Is it related at all to how you're exciting the system? If you put in a 10 hertz waveform into a linear system, are you going to see a 12 hertz signal out? No, you're going to see the signal that you're exciting it with, aren't you? If it's a stable system. And it will be either expanded or contracted and maybe shifted in time based on how that system is configured. And we're going to see the same thing happens to a discrete time system. It's just now an expansion or a contraction and maybe a shifting in time, and we want to now derive that or develop that based on what you already know or the insight that you have for an analog system. And then phrasing this or titling this discrete time frequency response. I've already tried to make the connection with what you are supposed to remember. or what previous knowledge you have. And hopefully, if it's not clear, it will become clear as we start working through this discussion. Or to make this more tangible, let's look at how will a sinusoid be filtered by a low-pass filter. That's our example to help illustrate this concept of frequency response. And you should intuitively already know what's going to happen if you have a low-pass filter and you inject a particular frequency into it. If it's within the pass band of your low-pass filter, what's going to happen at the output? And now you could be thinking, that was the bass drum if you didn't know, if you're listening. You could be thinking musically, right? Now, if you had some way of injecting a high-frequency, beautiful sound, maybe it has some high-frequency noise on it and you want to filter that out. We'll use a low-pass filter. Can you create a low-pass filter with an electric circuit? And the answer should be, in beautiful harmony, yes, right? And we don't need to filter that beautiful harmony. That was just great. So let's now design a low-pass filter. And we'll just keep it simple. We'll just do a first order. Design a first order low-pass filter. And I think I already saw someone's lips. I'm good at lip reading even when I'm blind. Okay. But somebody, I thought, said capacitor. So if we just had a capacitor, that's a first order, that's one energy storage device, this creates a first order low-pass filter for a given choice of a resistor and a capacitor C. Here would be our input waveform that we want to filter, and across the voltage across the capacitor is the output. And we hope that we've now low-pass filtered. And one way you can think of that is what? You're smoothing things out. You're sort of averaging things. And that's what that capacitor is doing. And we'll see that that same concept holds for our difference equation when we get there. Now, you probably all like to immediately move out of the time domain and go where? In analyzing this circuit. In the frequency domain. You like the frequency domain. It makes you feel warm and fuzzy, right? So if we convert this into the frequency domain, it looks exactly the same. It's just now we're using S's instead of T's. But we can now use some algebra instead of differential equations. Meaning, if we now take this into the frequency domain, we have the same structure. What's the impedance, except now we need to look at impedance values for our R and C. What's the impedance of a capacitor? 1 over SC. And we can analyze this with our favorite technique. If somebody wants to do a voltage divider, that's fine. Or if you don't remember how to apply a voltage divider, that's fine also. You can apply KVL. Any favorite analysis? All right, you don't know how to do KCL. Whatever you want to do, you can analyze this waveform. If we did a voltage divider, do you remember what that means? Yeah, you can say yes, right? You have a coin flip, but this would now be the impedance of the capacitor divided by the total impedance of the network. That's our voltage divider for this. And you can find this relationship in many different ways, but if we do it that way, we now have the capacitor's impedance, 1 over SC, over the sum or the total impedance in that series circuit, and that when scaling the input variables Laplace transform will give us the Laplace transformed output. And we may not like ratios of ratios. We might want to clean that up. We could get a common denominator in the denominator, which is SC, and then the SC's cancel, and we're left with a cleaner looking transfer function, which is now SRC, and ones everywhere else. This is now our low-pass filter that you should be able to derive on a napkin in an interview until you get a job, right? And maybe even beyond. Until you retire, you should be doing this, or able to do this. Do you see a time constant in this expression? Do you see a tau? There's our time constant, the RC time constant of that circuit. And that now we need to select in order to create the cutoff frequency of our low-pass filter. So let's select a bandwidth for this low-pass filter. Suppose that we now say create, this is step 2 in this process, create a low-pass filter with a bandwidth of, I'm going to put that about in there because I may not want to keep track of too many digits of pi. I may want to just round pi to 3. So there's my about. But it's close to 100 hertz. Now I want a low-pass filter with a bandwidth of 100 hertz, which means every frequency up to 100 hertz I'm roughly passing. If it was ideal, I would pass everything from DC up to 100 hertz, and then nothing beyond 100 hertz would go through. But this is a first order low pass, and so we have a smooth transition between, or in between the band, or the pass band of the filter and the stop band of the filter. But here, my cutoff frequency in hertz is 100. But in my transfer function expression, I'm actually dealing with radians, aren't I? Radians per second. And so my tau is in seconds, or now I need, or my S is in radians per second. I now need omega sub c, which is 2 pi f sub c, or 2 pi times 100, and that's now 200 pi, which I don't want to keep track of pi. It's already late. I'm already hungry. I just want to round it to 3, okay? And not say pi again. My mind is going somewhere else. So let's just say that that's 600, and we'll call that cutoff frequency good. This is where I'm getting the about. It's about 100 hertz for our cutoff. We can now use that in our denominator of our transfer function. Which was SRC plus 1, or that was this tau S plus 1. That's in time constant form. And we want now to select tau to give us a cutoff frequency of 600 radians per second. Or we now need to select tau such that S, or I'm sorry, this expression is or has a root when s is equal to minus 600. Or this now says s is equal to minus 1 over tau. And to have this 100 hertz bandwidth, approximately, we need s to be minus 600. We need to have a pole at that location in this first order transfer function. And now we can find the time constant. That's just the reciprocal of 600. That's 6 times 100, or 1/6 times 10 to the minus 2. I don't have my calculator, and it's getting late, so let me do this several different steps. I can now have 1/3 divided by 2. That's 1 over 6, or 1 times, that's not 1 over 2.3, that's 1 times the product of 2 and 3, so that now 1/3 is 0.333. I can find half of that instead of trying to remember what 6 into 1 was. Or this is now 0.167 times 10 to the minus 2, or tau is now equal to, shifting that decimal point by 2 places, to obtain a low-pass filter with a bandwidth of about 100 hertz requires a time constant of 0.00167. Or now h of s is this tau, s plus 1. Giving us a low-pass filter with a bandwidth of about 100 hertz. Now, if we wanted to verify that indeed that transfer function was consistent with what we think it is, what could we do? Or what might be a way to perform some verification of this low-pass filter in the S domain? And now you should know, if you've had me before, I'm looking for you to find the Bode plot of this transfer function. H of s, maybe to write it in a cleaner way, let's just describe tau as 1 over 600. So I now have 1 over tau s plus 1 is 1 over s over 600 plus 1. And that's the time constant form, which is helpful for the Bode plot. I may actually want to look at this also in a pole zero form, and this isn't very useful, but if I multiplied it by 1, then I would have the same low-pass filter with a bandwidth of approximately 100 hertz, written in pole zero form as 600 over s plus 600. If I'm sketching a Bode plot, I first need to know where do I sort of start my magnitude response. Which, if this is a low-pass filter, what's one of the key pieces of that magnitude response? Or where am I interested in a value? What frequency might I be interested in for that low-pass filter? Or at low frequencies, it might be nice to know what this filter is doing. And what's a low frequency? 1 hertz, let's go a little lower. 0, DC. Our DC gain is now found what? When S is equal to 0. That's dc. And what does that transfer function evaluate to, or what does it equal when we substitute S equal to 0? 1. And that's means that's comforting. Now if we put in a low frequency signal, we're going to basically get the same magnitude of that signal out. There's our DC gain. Now how do I use that information in a Bode plot? This is a first order system, and do I have any zeros in that transfer function? Was there a zero factor? Any value of S that causes that transfer function to vanish? No. So I don't have to worry about breaks going up in my magnitude response. I'm only worrying about things going down. And when is this transfer function going to break? Where is my pole? At what frequency? In radians per second. Is it that? Or are you toying with me? I now have a magnitude of 1 at low frequencies, and in decibels, or in dBs, or 20 log of that magnitude, that's 0 dB. I'm going to be flat in a straight line approximation for a Bode plot until I reach what frequency? Or what point? At 600, where I reach my pole, right? So now I'm going to get to 600, and then I will start going down. And how will I go down? At what rate? Wow, that really received a response. So apparently you do remember the slope. Not sure you could tell from that sketch, but this slope is going down at 20 dB per decade, where a decade is a factor of 10. Which means at 6,000 radians per second, I would be at minus 20 dB. What's the phase? So this is now H, the magnitude of H of our low-pass filter in decibels. What's the phase of that look like? The other half of the Bode plot sketch. Question? Where did the 7 come from? The 7, is that the 7 that you're seeing? This is my graphical talent. That was supposed to be, so the question was, where did you get a 7? That wasn't 7 minus 20. That was actually trying to indicate that I'm measuring the slope, the rise over run. And here I'm going down over run. So that's a kink trying to illustrate the slope. That wasn't a 7. Thank you for, yeah, so the slope of that curve is 20 dB per decade. Is that better? So I shouldn't have had it in the same color as my minus 20, because it did look like 7 minus 20. But the slope is, that's a slope symbol, and that's now minus 20 dB per decade sloping down, where this axis is now omega. What's the phase curve look like? Do you remember? At low frequencies, what's the phase of our transfer function? If I plugged in a small frequency, if I plugged in S equals 0, what's H's phase? What's the angle of H? 0 degrees, isn't it? It's a real number of 1, and 1 has a phase of 0 degrees. At high frequencies, what's the phase? Now I'm really looking at H of j omega, where I'm replacing S with j omega, and now I want omega to be really, really big. so that now that dominates in the denominator and it really swamps out the numerator. What's the phase of the numerator factor? What's the phase of 600? Or what's the angle, I should say, of 600? 0. Now I'm subtracting the phase of my denominator, which is 600 plus j omega, and I'm letting omega march off. That's going to produce an angle of 90 degrees, which in the denominator or downstairs, when I subtract it, it gives me minus 90 degrees. So I'm now transitioning from 0 degrees to minus 90 degrees, and where are those transitions occurring in the phase diagram? Here's 0 degrees. This is now the angle of h of j omega. It'd be nice if I could relate it to this 600. Here's 600. And you told me that eventually at high frequencies I will have an angle of minus 90. What's the angle at 600? Do you remember? That's actually halfway between these two extremes. And in a straight line approximation, we're saying, oh, start changing a decade before the break frequency, which in this case is 600, and quit a decade beyond that break. So if I can sketch this somewhat accurately, there would be 6,000. And now this would just be a straight line approximation. And right here, at this point, is halfway between 0 and minus 90, or there's minus 45. Now, I want to know what's going to happen if I inject a sinusoid into this low-pass filter. I'm now looking at, there's my system, which is a low-pass filter, and I want to know what's going to happen at the output if I put in a particular sinusoid at the input. And let's just select one. Let's say, suppose that the input in the time domain is 2 cosine of 500t. And just for something to talk about, let's call that frequency omega sub 1. Where is omega 1 on our diagram? Bode plot. It's 500, and it's somewhere on that omega axis. In the magnitude, where is it falling? If I had labeled other points, it would be a little bit easier to determine, but let's just say that 500 is right here. And in our straight line approximation, that's basically saying, oh, we shouldn't be changing the magnitude much of that 500, of that cosine wave of 500, but we know that we start to transition, so it will be less than just 2, which is what we're saying we're injecting. And what's the phase angle going to be? It's not going to be 0 degrees. It will be shifted in time, won't it? And it'll be shifted closer to minus 45 degrees than 0 degrees because of where 500 lies relative to 600. And if you remember from earlier classes, you could say that the sinusoidal steady state of the output is 2 times the magnitude of our system at the frequency that we excited the system at, which is 500, cosine. There it's moving at the same rate that we are exciting it, which was 500, plus the angle of our filter or system at that frequency. All of these are coming from the Bode plot information associated with that low-pass filter. And we're really just saying that we need to find h of s when s is equal to j omega 1, or we're finding the complex number of h of j omega 1 and finding its magnitude, and that's scaling the amplitude of our output, and we're finding its angle, and that adjusts or shifts in time where our output is relative to the input sinusoid. And we could find all of those also in a complex plane sketch in the S-plane, where this is now the real part of S. Here's the imaginary part of S, and we have a pole at minus 600, and we want to find what is, if we want h of j omega 1, and omega 1 is 500, we need to evaluate the transfer function h of j omega 1 at, on the imaginary axis at j omega 1, which is j 500. Or we are actually looking at that distance from the pole to that frequency and the angle that that pole makes at that particular frequency. And here's where the pole zero structure of our transfer function becomes more important. Now we have h of s equal to 600 over s plus 600, and we can now, from this pole zero diagram, we can actually visualize or measure with our ruler or dividers and a protractor the length of that distance and the angle. Or we are trying to find this complex number h of j 500. That's now 600 j 500 plus 600. We're just replacing s with j 500. Or this is now 600 in terms of our diagram. That complex number in the denominator is the length L sub p in polar form and an angle theta sub p. And now we should be seeing a hypotenuse. The hypotenuse is L sub p. There you go. So we need to now compute that L sub p, and that's just the Pythagorean theorem, the length of that hypotenuse. We go over 600 and up 500, and we need the length of that hypotenuse, which is now 600 squared plus 500 squared square rooted. And that's what will be downstairs for L sub p. Or we now have, in terms of h of j 500, 600 is easy. That's just 600 in polar form. But now we want the magnitude of 600 plus j 500, and we want the angle of that, which is the inverse tangent, or the angle that has a tangent of rise, 500 over run, which is 600. And if I had sketched that properly, you could inspect that and see that the hypotenuse is a little bit bigger than 600. It's 781. And the angle is 39.8 degrees. Doing the division and keeping track of the angle, which is 0 minus 39.8, now we can immediately, from that information of what the transfer function evaluates to as a complex number at that frequency 500, we can now say V sub O steady state is 2 times 0.768 cosine of, it hasn't changed the frequency, but we have we do experience a little offset, and that offset typically is measured in degrees, but if you're trying to compute that, you'll need to make sure that the argument, which the first term is usually in radians and that second one in degrees, they're consistent. Which says that if I now have a cosine of amplitude 2 at a frequency of 500 radians per second, and I push it through a low-pass filter of bandwidth 100, this is what I'm going to see out. The amplitude will shrink a little bit. It'll go from 2 to 1.5, and in the time domain, now the curves won't overlap. The bumps, the maxes and the mins will be offset by this phase shift of 40 degrees. And it will be delayed. That's the minus sign. Now what? Everybody's looking at their watch. They're already on Facebook. If you're on Facebook, I assume you're communicating with Euler. Now maybe you could start talking to Bodie after tonight. So you're going to have all sorts of Facebook friends, but we're trying to find a discrete time low-pass filter. We derived this transfer function for a continuous time system or an analog system of 600 over s plus 600. Let's see if we can actually find a way to describe that for a discrete time system. Starting then with what we have, our continuous time, and this is now 1 over tau s plus 1. But I can now cross-multiply, and I now have tau s plus 1 times v sub 0 of s, or the output, is equal to v sub I of s. That's in the frequency domain. Can we take that into the time domain? What's s? Multiplication by s in the frequency domain corresponds to what in the time domain? What's division by s? What's 1 over s as an operator? That's an integral. So what's the inverse of that? What's multiplication by s? That's a derivative. Meaning, if we now have tau s times v naught in the time domain, that says we want the derivative of the output scaled by tau. We're just inverse Laplace transforming that expression, where we now have tau v naught prime of t plus the inverse Laplace transform of capital V naught of s, which is just v naught of t, equaling the inverse Laplace transform of capital V sub I is v sub I of t. And this really is just a differential equation that describes the characteristics of our low-pass filter of a bandwidth of about 100 hertz. This is our time domain differential equation. And its first order. And we were able to find that from our first order transfer function. We're doing things sort of by the seat of our pants tonight and quite often in this class. So we want to now take this and take it into the discrete time setting. We want to try to approximate this differential equation by a difference equation. So let me say this is now a crude discrete equivalent. And by that, the way that we are going to go from the continuous time setting to the discrete time setting is to approximate this derivative by a difference, by a finite difference. Meaning, let's now let this v naught prime of t be, which is now the derivative of our output, let's approximate that with v naught one time step ahead of the present time, which we will now denote as little n plus 1 times t, minus v sub naught of t at the present time, which is little n capital T, and now my dt is just the time difference between those two arguments, which is really just n plus 1 t minus nt. So there is a small difference in my output by the sample period, and the time difference is just the difference in time between those two arguments, n plus 1t minus nt. Or this now allows me, with this rough approximation, to say that wherever I see a derivative in the time domain, or in the continuous time domain, I'm going to approximate that by v naught of n plus 1 times capital T minus v naught of nt all over what's in the denominator. If I simplified, if I distributed that sample period throughout that n plus 1 and subtracted nt. That's just t. What is the value of that t? Or what is t, other than the first letter of my last name? Can't use that on the exam. I guess you could. Maybe you'd get some brownie points. I don't know. Maybe it would lighten the mood when I'm grading. But this is the sample period. Do we have any idea how we would find that on the exam? If I now said, oh, you have a low-pass filter with a cutoff frequency of roughly 100 hertz, we know it's 600 radians per second, can you find what capital T needs to be? What did we say about bandwidth and the sample period before? We know right now that omega sub c is 600, right? That's our bandwidth. How did we relate that to the sample frequency's bandwidth or value? Do you remember our, somebody have a ruler? Then I would do a ruler thumb. What was our rule of thumb? Right? So what was our rule of thumb between the bandwidth, or the closed loop bandwidth, and the sample frequency? And now you'll be seeing this ruler and somebody's thumb. But a rule of thumb, what was that? 30 times. So now we know what omega sub s is. It's 30 times 600. This is now 30 times omega sub c. Or this is now 30 times 600. And that's now 18,000 radians per second. How do we find a capital T from that? What were you supposed to remember until you graduate, or until you retire, not until you graduate, until you retire? 2 pi f. So there's our sampling frequency. And how is the f sub s related to t? It's the reciprocal. So this is now 2 pi over cap t. So that now we know that capital T is 2 pi over omega sub s. And we know what omega sub s is. That's this 18,000. So t, again, I'm doing some approximating. It's 2 times, and if I go less, that's better. I'm now shrinking my sample period. Pi is 3.14. I'm just going to forget the fractional part and just say that's 2 times 3. And 18,000, that's going to be 3 times 6 times 1,000. So that I can now sort of clean this up, or I now have 1/3 times 10 to the minus 3. Or my sampling period t, when it is called for, will be 0.000 repeating 3. That's my sampling period. And that better be less than my time constant. What was my time constant? Wow, really? 0.00167. So it is. It's seeming consistent. So now let's convert the differential equation, that first order differential equation, into a difference equation using this crude approximation of the derivative. Convert the differential equation, and now I need to spell some of this out, because if I said DIFF, you'd go, is that differential or difference? So it's differential equation, I can abbreviate that, into a difference equation, where I now had this tau, V naught prime of t plus V naught of t equal to V sub I of t. And approximating the derivative, I have tau times V naught of little n plus 1 cap t minus V naught of little n cap t over t plus V naught of nt equaling V sub I of nt. So I've sampled my differential equation, replace the t with little n capital T. I'm now sampling what? Every 0.00033333 seconds. So I've sliced this up pretty fine in terms of the time axis. Yes? So the question was, we approximated pi a couple of different places. Do they cancel each other out? Not necessarily. We used a pi approximation to approximate our bandwidth of the low-pass filter, and then we said, oh, let's find our capital T, the sample period, and we approximated pi. They may actually sort of cancel out, but our bandwidth is not exactly 100 hertz. It's still approximately 100 hertz. So I don't know what you mean by a cancel, but if we carried the 2 pi through, it would have just meant that our resistors and capacitors would have had these weird numbers maybe relative to the bandwidth of our filter. So it doesn't really matter. We're just making that approximation consistently throughout, but I'm not sure that they really cancel each other out, the effect of that. But if we now multiply everything by capital T and divide by tau, hopefully you see that we have V sub 0 of n plus 1 cap t minus V sub 0 of nt plus capital T over tau V naught of nt equaling capital T over tau V sub I of nt. And now we simply have a difference equation. If we solve or push everything on the other side of the equality and keep on the left-hand side the advanced indexed version of our output voltage, we now have V naught of n plus 1 capital T equaling 1 minus, that minus V naught is on the other side, so that gives us our 1 minus capital T over tau V naught of T plus capital T over tau V sub I of nt. And if we plug in the numerical values that we've calculated for capital T and tau, now this really ends up being, and here's maybe where they might have sort of canceled each other out. Let's just say that this is now, we'll approximate that as 1 minus 0.2, or this is now 0.8, where this is now 0.8, and this I'm approximating as 0.2. So that now we have a first order linear difference equation for a low pass filter that looks like V naught of n plus 1 capital T equaling 0.8 V naught of nt plus 0.2 V sub I of nt. This is now a first order difference equation that actually produces a low pass filter characteristic, that produces a low pass filter with a bandwidth of approximately 100 hertz. How hard is that to implement? If somebody now gives you a time domain waveform, they're giving you lowercase v sub I. And it needs to be sampled at what sampling period? You know capital T, right? It has to be 0.00333. So if they gave you an analog or a continuous time signal, you would have to sample that. Now if they give you that sampled waveform, you could put it in for V sub I, and you could start at n equals 0. And you'd say, oh, in the first sample, now I need to, and you might forget about the transients. Let's just initialize the output at 0 and then propagate that through. What does this say to do? It says to take 20% of that input, add it to 80% of the previous output, and make the new output value. What are you doing? You're really just sort of a moving average of the waveform to get a filtered version of that input signal. It's just a first order difference equation that now is operating as a low pass filter. Let's see if we could do that relative to a given or the same kind of sinusoidal input. We had a cosine waveform. What if V sub I, now instead of V sub I of t, we're sampling it, so it's now V sub I of nt. It had an amplitude of 2. It was a cosine. What was our frequency that we did in the analog case? 500. So this is now 500, little t, but little t is being sampled, so that now that's little n capital T. And what is capital T? So we can put that in. We can multiply 500 times this 0.000333. And that gives us now an argument of our cosine of something, an angle times n. Or we now have our input is 2 times the cosine of 0.1665 in. And we want to know if we use this in this difference equation, what's going to happen? What will we see at the output? Where here we looked at the argument of our cosine. Let's just make that clear. That was theta sub d, which was omega sub d capital T, where omega sub d in this case we were calling omega sub 1t, and that was now the 500 times the 0.000333. That's where that came from. And we want to know what's going to happen eventually in the sinusoidal steady state. What will be, or can we find, V sub 0, the output voltage in the sinusoidal steady state of NT? Have I already answered that? Can we find V sub naught sinusoidal steady state? We could if we just iterated, right? If somebody's patient, we can just sit there and iteratively compute the output from, now we have a filter that's just a linear difference equation. We can compute what that output's going to be. We could also do it if somebody gave us the transfer function and said, what's the transfer function look like at 500 radians per second in the z-plane? Let's see if we can find the transfer function of this first order difference equation. Pardon? So now we are not going to use the 1% settling time. We're trying to, it's never going to settle, is it? We now are exciting this system at 500 radians per second, and it's just going to eventually get to a steady state, but it won't be constant. It's a sinusoidal steady state. And what's it shaking at? Faster than I am, right? It's 500 radians per second. Let's see if we can now find h of z, because h of s before was helpful because we could find the complex number h of j omega and use that in our determination of the sinusoidal steady state. We can actually do that here if we have our transfer function. We now have this difference equation . What if I z-transform that? What do I obtain on the left-hand side if I z-transform this waveform that's advanced by one sample period? What corresponds to an advance of one sample period in the frequency domain? A z, right? An advance is z, a delay is z to the minus 1. Here we have an advance, that's the n plus 1. Meaning, in the left-hand side, we can say, oh, the z-transform of that is now little z times capital z-transform of little v naught. What happens if I z-transform the first term on the right-hand side? That scaling just factors through the z-transform definition, and what's the z-transform of little v naught? That's too easy, isn't it? We just have to hit the shift key on our typewriter. We just need to capitalize it. We now have capital V naught of z. Likewise, we now have capital V sub I of z. what are we trying to do? We're trying to find this ratio of V naught over VI to find the transfer function. Or we now have Z minus 0.8 V naught of Z is equal to 0.2 V sub I of Z. Or the transfer function now, V can be found by dividing both sides through by this factor Z minus 0.8. And our transfer function for the discrete time system is now this h of z, and that should be relatable to this block diagram. And what I was unable to get to, which I may do after the fact, is start to illustrate what this looks like in terms of its frequency response. But can you sketch the pole zero diagram of h of z? Where's your zero? Finite zero. You don't have one. Where's your pole? 0.8. Is that inside the unit circle? So this is a stable system. It better be. It was a low-pass filter. We'll pick up somewhere close to that on Monday.